Okay then. Well, hello everybody, and welcome again to the University of Washington Astrobiology Seminar Series for this spring quarter. Our guest today is Professor Siegfried Franck from Potsdam University. And Siegfried has a very long history in both physics and geophysics. He did his physics degree in the University of Leipzig and got his PhD in 1978. He then did what he describes to me as a second PhD, because this is required in the German system, and eventually became a lecturer in 1984 at the Central Institute for Physics of the Earth in Potsdam after completing his second PhD. In 1989, he was appointed as a professor of geophysics, and since 1997, he has worked at the Potsdam Institute for Climate Impact Research in the field of Earth system analysis, focusing on planetology and astrobiology with a particular interest in habitability and long-term habitability of terrestrial planets. Since 2004, he has been the professor of coevolution of the geosphere and biosphere at Potsdam University, and today he will be talking to us about Earth system analysis and its applications to astrobiology. So, Siegfried?
Ladies and gentlemen, first I want to thank Vicky for inviting me to Seattle and to have the possibility to give a talk. The title of my talk was already announced. I must say the title is not so spectacular, and today we have the day of the Earth. And I prefer that I should have used the title The Search for a Second Earth at the Day of the Earth. But this is not so very good, but it describes a little bit the topic I want to speak about. Namely, I have two parts. First, to investigate our planet Earth and the long-term evolution of the geobiosphere, a term that was introduced by Vernadsky, the famous Russian scientist. And the second deals with habitability and extrasolar planets. So I have two parts. Next remark is the following, that after this pizza discussion with your students and your students from the faculty, I have the impression that maybe my talk is too simple, but Vicky told me that I should have a level for all students, and so I hope this will not be the situation that you know all about it, even the students. Nevertheless, I want to start with the next figure. We do Earth system analysis, and Earth system analysis means to investigate the Earth as a system. And if we do this at the long time scales, we investigate the Earth as a system of certain components. And these components are, for example, the deep interior of the Earth, the oceanic crust, the continental crust, the atmosphere, the hydrosphere, and of course the biosphere. And in the framework of the modeling, we try to investigate how these components develop under a so-called external forcing. And in the case of the Earth, this external forcing is the insolation, the radiation from the sun, which changes over time, as we know, from the faint young sun paradox. Or in the case of extrasolar planets, we have another central star. And to do such modeling, we have to investigate a process that is involved in this interaction between central star and planet, and this is the so-called global carbon cycle. The global carbon cycle, you know, in our institute, scientists investigate also the carbon cycle, but on shorter time scales. For example, the carbon cycle between the biosphere and the atmosphere. The biosphere takes carbon from the atmosphere, makes photosynthesis, and creates biomass. And let's say after 100 years, such a tree can die, and the CO2 goes back to the atmosphere. This is also a carbon cycle. But our carbon cycle has a very, very long scale. It describes the carbon in the atmosphere, how it takes the greenhouse effect, and it describes the process of weathering. That means CO2 is dissolved in raindrops as carbonic acid, and this carbonic acid interacts with the silicates from the continents, and within this chemical reaction we have some products that are produced by small rivers and larger rivers to the sea, and in this case carbon is transported from atmosphere to the ocean. And in the ocean it can make certain reactions, it can settle down to the oceanic crust, it is transported to subduction zones. Here we have so-called metamorphic reactions in about 100 kilometer depths, and a part of this goes back to this shortcut via back arc or andesitic volcanoes to the atmosphere, and the other part goes down in the mantle, and in the framework of plate tectonics it may come back to the mid-ocean ridges and go again into these so-called surface reservoirs. And this takes very, very long. If one could mark a carbon atom, this process would take about 800, 900 million years. But this is the present carbon cycle, and we have some knowledge or also some speculation how this carbon cycle was in the past. And we know in the past, according to the Fate-Young sun paradox, the luminosity of the sun was smaller, of about 25% than the present value. But in the framework of this, there was much more CO2 in the atmosphere, and the greenhouse effect was about 4 times the present effect. But we know in the Archaean we had no such trees. We had only microorganisms, so the biofilms. So there was another process of the biogenic part in the system. And on the other hand, the continental era was about only 10% of the present one, and the spreading rates have been much larger than today, about 4 times as larger. On the other hand, the mean mantle temperature was about 200 degrees higher. Though these are values that we know and that we should recover without our modeling model. But we don't not only look into the past, but also into the future.
Excuse me, why was the spreading rate larger in the past?
Because the Earth was much hotter, and the heat flow was higher, and the spreading rate is related to the heat flow. And we can speculate or even calculate how will be this carbon cycle in about 1 billion years. The luminosity will grow up to about 10%, to 110% of the present value. The greenhouse effect may be about only 90% of the present value because there is less CO2 in the atmosphere. We don't know what will be in 1 billion years with the biosphere. How will it look, and what type of biosphere will be there? If the continents grows with a second rate, they will have an area of 40% larger than today, and the mantle temperature will have lowered down for about 50 degrees Kelvin. So this is the long-term future. And now the picture I showed you was a global carbon cycle in the language of geoscientists, of geophysicists, and geologists and mineralogists. But here I have this same cycle in the language of a modeler and here of a mathematician. It's the same which I just showed on the pictures before. Here we have a so-called box model where we have 6 boxes, namely a box atmosphere and ocean, continent, seafloor, mantle, biosphere. And you know, if biosphere dies, not the whole carbon goes back to the atmosphere in this decay, but there is a deposition of organic, of reduced carbon, less than 1%, and this is called kerogen, and this is deposited organic carbon. So we have 6 boxes, And the carbon cycle consists of the exchange of carbon between these boxes by various processes which are written here. And the mathematician would write down these differential equation for these 6 boxes here: mantle, ocean and atmosphere, continents, ocean floor, biosphere, kerogen. And this is an equation describing the cooling down of the mantle and calculating this heat flux, which you asked for using it to describe the spreading rate. So I show you a little bit larger the relation. For example, this term here is a recasting with very little subtraction rate. So every term is related to a certain process, but I cannot explain all the processes in detail because lack of time. So I will show you it a little bit quickly. You can imagine that, for example, this is a mathematical expression for this error, for this exchange from the seafloor to the atmosphere and ocean, and so on. Weathering. Precipitation means the falling out of carbonates in the ocean. Hydrothermal reactions here. Hydrothermal reactions take CO2 from the ocean and deposit it at the seafloor, and so on. And now, if we use the system of equation, we can calculate the time evolution of every reservoir of carbon over Earth's history and into the long-term future of the Earth. And this is shown here. We have green is the mantle, atmosphere and ocean are red, ocean floor is blue, kerogen is black, is here, and continents are magenta. Though we have some special features, for example, that during the long-term evolution of the Earth, because of the increasing solar luminosity, CO2 is transferred from the surface reservoir to the mantle, as we see here. And the other reservoirs have a certain time evolution. I don't want to speak about in detail at this point, but you have to believe me that this is a result, and we can use single results, for example, for calculating the atmospheric CO2, which is here. So we have the general results that in the Archaean we had a high level of CO2 in the atmosphere because solar luminosity was low, and this goes down with evolution into the future. This is today, this is the beginning, this is today, and this is about 2 billion years in the future. And this gray shaded era means that within this era the CO2 content of the atmosphere corresponds to a mean global surface temperature between 0 and 100 degrees Celsius. This is a surface temperature, the corresponding, and we see according to the continental growth model, we had first such an effect, but we had very high temperature, but then temperatures went down, and at present we have, in the geological sense, we have a minimum of atmospheric CO2, and in the surface temperature, and in the future it will go again to higher values. So this is a point I don't want to speak in detail. This is a ratio of carbon in the kerogen and in the carbonates. That means the ratio of organic to inorganic carbon, which was investigated in detail by the main famous German geoscientist from Mainz. And here we say that this ratio is about 1 to 4. That means 1 organic atom of carbon corresponds to 4 inorganic carbon atoms. Minkowski was the name of this man. And here this curve is taken from the from the famous book of the American scientist who works in New York.
Excuse me, can I just ask another? I just want to be clear. The only things that is changing with time in your model is the heat flux from the Earth and the sun insolation?
Yes. These are the internal and external forcing.
These are the only forcing.
And of course, the era of continents.
Right.
The era of continents.
So you take that as from the geological record?
I take it from the geological record. I come back to this.
How does your the carbon fractionation in kerogen go from 0 to sort of a step increase at maybe 3?
It goes here from 0 because at the beginning we have no biosphere, or no big biosphere.
So you're just turning on the biosphere.
Yes, this is a mathematical artifact, but here it is about this. But then during dying out, there is another, let's say, artifact.
Do you ignore anthropogenic carbon dioxide? So what metals that is included?
Anthropogenic is not included. It's too small for this effect because the let's say 100 years of anthropogenic introduction of CO2 in the atmosphere. These steps are about 10 or 50 million years, the time steps.
This is the real global warming on Earth Day.
You see, today we had really the lowest mean global surface temperature. And of course, we have been asked by people, oh, if this is right, you may be, let's say, somebody that can speak for anthropogenic introduction of CO2. But the argument is the following. The main problem of anthropogenic introduction of CO2 to the atmosphere is the rate. And the rate is about 100 times higher than the natural rate from volcanoes. This is if mankind would burn the fossil fuels very slowly, like it was synthesized in nature, it would be not a problem. But the rate is a problem.
Professor Franck, one more quick question. At the end of the runaway temperature, presumably this is caused by the death of rooting plants, and so you no longer get feedback from plant erosion and weathering?
Where?
Yep. Assuming if you hit...
The main reason of this is the increasing sun. At this time, the system can make a process of self-organization. We have the increasing sun, and we say here the surface temperature is mainly determined by geophysics, by the heat flow and by the era of continents. But here the increasing sun overcomes all the other effects if you look at the certain values and makes all other things down.
And it gets worse with the loss of biotic weather in that too.
This is an additional effect. But in the picture I just showed you, we had a very, very rough biosphere. We had a biosphere that had two properties. It can exist between 0 and 100 degrees Celsius, and the second condition is there must be an atmospheric CO2 content of more than 10 ppm CO2, which is the lower limit for C4 plants, as the present biosphere is. But we know the biosphere is more complicated, and therefore we introduce three types of biosphere, namely procaryotes, the most simple type of a biosphere, which have no core in the cell, eukaryotes, simple eukaryotes or protists, which are one cell living beings with a core, and of course the complex biosphere, which consists from multicellular complex living beings and has plants, animals, and fungi. And for doing the modeling, we introduce these three types, and the temperature tolerance windows for these, so the prokaryotes are very robust. These numbers come from discussions with academician Zavazin from Russian Academy of Sciences. Then eukaryotes are a little bit more sensitive. They exist in this temperature range, and complex multicellular life exists in this temperature range. And the sensitivity to CO2 in the atmosphere is all the same as in the former biosphere. That means lower limit for photosynthesis is 10 ppm. And then we can model so-called biological productivity for these three types. And we have a further effect. We take into account that the biosphere can have an additional effect on weathering. It can enhance weathering, and this is described by this beta. This is the usual formula for weathering. This is activity of protons, and this is the Arrhenius factor. And we assumed that the prokaryotes and eukaryotes have no additional effect of weathering. If we put in here 1 for beta 1 and beta 2, we have 1. But the complex life forms have an additional effect on weathering. We can imagine, for example, that a tree has a strong effect on weathering by producing soil and so on. And if we look at the results, we see here the time from 3.5 billion years in the past, this is today, into the future. And this is the mean global surface temperature, this green curve. And we see in the Archaean we had very high temperatures, and this is in good agreement with observations from Knaut and Löwe from Harvard, which observe oxygen isotopes O16, O80 ratios, and then it falls down. This is a continental growth model for the Earth according to Conti, so we have certain periods of enhanced and not so strong continental growth here. And these effects are connected to these events in the continental growth. And here we have effects that we have two stable solutions, an upper and a lower, with upper and lower temperature. And then we have here this affects the Cambrian explosion, where it goes down. This is today, and then we have the future. And here we have the cumulative biosphere pools, that means the biomass. Red means from prokaryotes, green from eukaryotes, brown from complex multicellular life. So at the beginning we had only prokaryotes, here is the appearance of eukaryotes, and this is really a Cambrian explosion like the complex life organism come into play, and then they go down. Today we have nearly 1/3 of this, 1/3 of this, 1/3 of this, and in the future this part goes down, then the eukaryotes, and at least the prokaryotes. This curve is the atmospheric oxygen content, but because lack of time I don't want to discuss it here. We can speak about this in the discussion. And these results can be also illustrated here. This is a stability diagram. Here we have this biogenic enhancement factor. Here is time. We have found this enhancement factor of about 3.6. Here we have only prokaryotes. Then comes the green karyotes into play. Here is already a metastable existence of the multicellular life possible. here we have at least the multicellular life. But when they die out in the future, years to date, the dying out of the complex life forms is a usual form and not such an explosion like in the past. And this is the dying out of eukaryotes, and this is the ultimative lifespan. That means the dying out of the prokaryotes. And this has a good relation to the famous book of Peter Ward and Donald Brownlee, namely The Life and Death of Planet Earth. And if I remember this book, these authors also propose that these types of biosphere die out in the reverse order as they appear. First die out the complex life forms, then the eukaryotes, and at least the prokaryotes. But according to our results, there is no complete symmetry, because the complex life forms die out in the usual way and not in the framework of a so-called anti-Cambrian implosion. That means the disappearance of complex life forms is not like an implosion in relation to the explosion, but is in the usual way as the eukaryotes appeared on the Earth. And this is the difference.
The 3.6 factor, where does that come from? Obviously, that's quite important as to what the value there is.
We have, of course, may test it. It makes no qualitative, but of course quantitative change. And it was used to make this time of the Cambrian explosions 540 million years ago exact at this time. So you can shift it a little bit. So if you work in this field, you will believe me that this. So we had the end of the biosphere as proposed, but of course we also can speculate about the end of the Earth as a planet. And in May, we have invited our colleague Manfred Kunz from Archaean University, who has also worked in this field, and he will give in Potsdam a talk, the lifespan of the Earth as a planet. And in last week, there was an article by Klaus-Peter Schröder and another scientist in Monthly Notice of the Astronomical Society about this problem. And of course, I cannot speak about this. This will be in about 7, 8 or so billion years, 5 or 6 billion years. You know, the sun becomes a red giant in about, let's say, 5 or 6 billion years. And this is then the ultimative end of the planet Earth. And now I come to the second part, namely to the habitable zones and the search for the second Earth. And I use this picture from Antoine de Saint-Exupéry from this book, The Little Prince. And if you read this book, there is a situation where the little prince asks a friend where he should settle down, and the friend gives him the advice to settle down on planet Earth because the Earth has a good reputation. In this sense, this book is the first definition of a habitable zone. Therefore, I use this as a starting point. Of course, in the scientific field, definitions of the habitable zone started later and in a more serious way, for example, by Wang, Dole, Shklovsky, and Sagan, and others. And later on came the famous modeling papers of Hart and, of course, of Jim Karski and his colleagues. And the definition of the habitable zone is a range of distances around a central star at which Earth-like planets maintain conditions sufficient for the existence of life at the surface. This would be the green habitable zone. And of course, for doing this, we have a simplified Earth system model. Not as complicated with the 6 reservoirs, but it is sketched here. We have, of course, not the sun, but another central star, and the internal forcing. We have a continental growth model, not such detailed like the Conti model, but maybe linear growth or constant continental era. And we calculate the heat flow, and the physics behind this model is that the atmospheric content of such a planet has sources and sinks in the biosphere. The sources are volcanic sources, which can be calculated from mid-ocean ridge and spreading models. The sinks are the weathering, which I explained already, that carbonates and silicates of continents react in a chemical way with the atmospheric CO2. And of course, the biosphere takes out CO2 from the atmosphere, and when it dies, it gives back CO2 to the atmosphere. So this is the main idea between such simplified models. And here we use this Conti model again for the Earth, because we start with our solar system, and later on we use linear models for constant models. And of course, here's our definition of a habitable zone. In our definition, the habitable zone is a range of distances around a central star where biological productivity is a biomass that is produced on a planet per unit of surface and per unit of time, and depends on the atmospheric CO2 and on the surface temperature, is larger than zero, of course. When biological productivity is larger than zero, we are in the habitable zone. Here it is zero because usually it's too hot. Here it's zero because usually it's too cold. And we use a temperature interval between 0 and 100 degrees. Again, 10 ppm as a minimum. And from planetological arguments, we also can have a maximum of 10 bar. And when we apply this model for the solar system, we have here the Sun, here's Venus, here's Earth, and here's Mars. And this is today. This is 1 billion years in the past, and this is 1 billion years in the future. And what do we see? This is the lower boundary of the habitable zone, and it shifts slowly outward with time. And of course, this is to understand because the solar luminosity grows on, it becomes hotter, and the inner boundary shifts outward because it comes to hot at such a place. And up to this time, this is also the case for the outer boundary, and also in the models of geocasting we have this. But here, the growth of continents comes into play. If the continents grows, the continental era makes more area for chemical weathering reactions if we have larger continental era. And so more CO2 is taken out from the atmosphere. And therefore the outer boundary shifts inward. This is today. And then we have a point where the habitable zone vanishes. And this is the ultimate lifespan. And we can imagine that if the Earth could be shifted about 8-10% more than the present distance from the Sun away, then it would be at this, let's say, optimum distance. Here you have in this way, it leaves the habitable zone at the inner boundary in about 500 million years in this model. And we see in the present time only the Earth is in the habitable zone, it's near the inner boundary. But we should be careful. 1 billion years ago, we cannot say Mars was habitable because this model was for the Earth. We must say correctly, 1 billion years ago, the planet Earth at the present position of Mars would have been habitable. Yes? This would be the correct answer. For this, we should have a planetary evolution model, especially for Mars, and investigate this. And if we go to other central stars, now I can this make quickly, we should use the Hertzsprung-Russell diagram. That means the luminosity, temperature relations, independence of the star mass, and we know low mass central stars are very, very long, on the main sequence. This is the main sequence, and the difference between these points is 1 billion years. Here is the Sun. It's 4.6 billion years old, and it has about the same time in the future on the main sequence. And we also observe if we have more massive star, for example, a 2 solar mass central star is only a little bit more than 1 billion years on the main sequence. Only a short time on the main sequence. It's not a news for you as astrophysicists. And so we can calculate this habitable zone for all different central star masses. Here we have an example for a solar mass, but not the continental growth model of Conti, but a simple model. And we have again this effect that at this point we have a shrinking of the outer part of the habitable zone and an automatic lifespan. For an 80% central star, the habitable zone is more near to the central star, and it does not shift so very much, but here we have again this effect. But for a 120% central star, the habitable zone is more outward than 1 astronomical unit. Here is the distance in astronomical units. But according to the short lifetime on the main sequence, this stopped because at this point the Sun becomes a real giant. So we could use this, and now I come to a next point, namely the so-called dynamical habitable zone. Up to now, we did not investigate extrasolar planetary systems in a special way, but if we look at the special extrasolar planetary systems where there are more than 1 extrasolar planets, there may be the effect that there is a giant planet, like here, that has a gravitational influence on the habitable zone. And for example, he can force that there are unstable orbits of other planets within this range in his neighborhood. And the rest of the habitable zone is called the dynamical habitable zone. So usually the dynamical habitable zone is smaller than the ordinary habitable zone, or at least it could be the same value if this is more outward. I think it's to understand, to calculate the dynamical habitable zone. And this range can be calculated with help of the Hill radius of these giant planets. And we have used a catalog and found 86 exoplanetary systems where we found all the data, for example, mass of the giant planets and mass and luminosity and age of central star and effective radiation temperature, which we needed to do the calculation. And from these 86 investigated systems, we found that more than 60% have a non-vanishing width of the dynamic habitable zone. You know, the dynamic habitable zone is the usual, but under the condition that there are no gravitational perturbations of orbits of possible Earth-like models. And here is the age of these systems, and here are the names of these systems. And we investigated Earth-like planets with a constant ratio of continents and oceans. Here we have only 10, 20 or 30% continents. These are so-called water worlds, like in the movie of Kevin Costner. And these are land worlds where we have 90% continents. And this has a strong influence on habitability, as we found out. And here we see these colors, and we see that always the water worlds have a larger width of the dynamic habitable zone. And the most important finding for us was the fact that our solar system is at place 19. So if we use this definition, that the width of the dynamical habitable zone is a measure, let's say, for the habitability in the system, we found 18 systems that have better conditions for finding a second Earth as in our solar system. And this brought us to the idea that this is a, let's say, manifestation of the mediocrity principle, which was introduced by Copernicus when he went from the geocentric to the heliocentric system, that he said the solar system and life on Earth are about average, and life will develop by the same rules wherever the proper conditions and the needed time are given. So Earth is nothing special, or solar system, but it's mediocrity. Now I come to the point of calculating the number of habitable planets in the Milky Way, and the first way to do this is with the help of the famous Drake formula of Francis Drake. He wanted to calculate the number of intelligent civilizations in the Milky Way. And so he proposed to do this with the help of this formula: the total number of stars in the Milky Way times the fraction of stars that have planets, times the fraction of stars that have Earth-like planets, times the fraction of Earth-like planets that are in the habitable zone, times the fraction of habitable planets that develop life, times the fraction of habitable planets that develop intelligent life, times the fraction of intelligent life that develops radio technology. And here is a normalized mean lifetime of an intelligent civilization. You know, this is a topic of discussions, and every scientist can use its values. But we proposed that for calculating the number of habitable planets, we only need the first 4 factors. And these 2 have been mixed to 1 factor. So we found that according to the investigation of extrasolar systems, we have more experience about these values. The number of total stars in the Milky Way is 400 billions. Then we assume that the fraction of stars with Earth-like planets is about 1%. And this could be calculated from our investigations of habitability. I cannot show it in detail. We could talk about this in the discussion. And we found that there is a fraction of about 1.2% of Earth-like planets in the habitable zone. And this gives us a number of about 84 or 480 million, 84 48 million, about 50 million, excuse me, 84 million of habitable planets in the Milky Way. So this is a rather simple calculation. If you have another feeling of numbers, you can put it in. But there is another method to calculate these number of habitable planets with the help of a convolution integral. A convolution integral means it's a time integral where we calculate the number of habitable planets first from the planet formation rate at a certain time t prime times the probability that an Earth-like planet that appeared at the time t prime is even in the habitable zone at a later time t. This is this convolution. And this could be taken from some investigations of Charles Leineweber from Sydney, and this could be taken also, I will not speak in detail, but if we take this integral, we have the number of habitable planets at a certain time t. And here we have this planet formation rate normalized to the Milky Way. So this is present, this is Earth's origin, this is Big Bang. So at present we have about 1 present. We have a planet formation rate of 0.10 per year. And here we have the calculated number of habitable planets, and at the beginning we had no material, so the planetary formation rate was 0 and also the number of habitable planets, but then it came very high and it's down, and now we have here a value in the order of, let's say, 30 million. We had 48 in the simple calculation, here 30 million. And what is also interesting is that near to the time of Earth's origin, we had a maximum number of habitable planets in the Milky Way. And this brought us to the idea that at least if panspermia, interstellar panspermia, was possible at all, then it was most probable at the time of Earth's origin. This is a consequence of this curve. So we tried to use this to do some quantitative estimations for the rare Earth hypothesis of Peter Ward and Donald Brownlee, and we calculated the rare Earth factor, namely the number of habitable planets which are appropriate for primitive life only, to the number of habitable planets which are appropriate also for complex life. And doing this, we did a similar calculation like I have shown before. We have the number of habitable planets here with primitive life, and here with complex life. Here's Big Bang, here's today. And we found a difference of 10 to the power of 2. That means at present we have 100 times more planets with primitive life than with complex life. But I should say that this is in any way a lower bound, because there are a lot of factors that are discussed in the book by Peter Ward and Donald Brownlee that we up to now did not take into account. Here we took only into account the poisoning effect of too high CO2 content and the sensibility to the temperature tolerance window. One should take into account the lack or the existence of a magnetic field and many other points. So this is always a lower bound, and in future estimations this number will become larger.
But it's remarkable that the ratio doesn't change that much over time.
Not that much, yes. Of course, here after the appearance of complex life.
Yeah.
Here it is finite ratio.
Oh, no, I mean...
Yes, yeah, you mean this, yes?
Yeah,
we go down. Yeah.
You take those two guys much more seriously than we do.
Well, I come to the last picture. You can imagine that these investigations, for example, in investigating the specific extrasolar planetary systems, we started with the so-called 47 UMA system. You know, UMA Ursae Majoris, the 47th brightest star in Ursae Majoris, which was discussed some years ago as a first system that has a little bit a similarity to the solar system, because they discovered two giant planets a little bit outside, comparable to Jupiter and Saturn, and the habitable zone was a little bit inside, like in the solar system. And therefore we investigated this and found out that water worlds are preferred. And so Nature didn't publish our original paper, but they published an article about our original paper, International Journal of Astrobiology. And so there have been a lot of media that reported about this. This was the top, and this is the lower end. The Zeitung is the most deepest yellow press in Germany, like the British Sun. And they came to our institute. It was in August 2003. I was on holiday, and this is my co-worker, Werner von Bloh. And Bild-Zeitung came and took a photo of him. And here, the building of our institute is a former Astrophysical Institute Potsdam, so they even had a telescope and reported about this. And the main point is, there is a slogan, "Bild brings it to the point." If they would have asked me to write about or to talk about this possibility of the existence of a second Earth in 47, Ursae Majoris in German, großer Bär. Ursae Majoris means großer Bär, big bear. And I would have said there could be special conditions that under certain conditions maybe there exist and so on. But they write, he says, the aliens live in the moon. So he brings it to the point. And this is my closing remarks, and I thank you very much for your attention.
A lot of your models seem to depend on having progressive continental growth built into an expanding continental area through time. There's a substantial fraction of geoscientists who disagree with the Condi model that that's based on and would argue that continental area on Earth has probably been pretty consistent since 4 billion years ago. And I would also argue with the Schwarzman model for temperature evolution as well, arguing that that's been roughly constant through time. If you were to change the inputs into your model and have constant continental area and relatively constant surface temperature, how would that change things?
First, maybe I did not explain it in detail also. We use the Condi model for the Earth. Of course, because we believe in the Earth. But for the extrasolar planetary system, we usually used the model of constant continental area, but of course certain amounts. For example, if I may go back. Here, we always, you can assume if the continental area is, for example, only 10%, if we have a water world, then we have this result with the blue. We have no growing of continents in this, because we don't know practically nothing about these extrasolar planetary systems.
Yeah, but I was referring more to your terrestrial models of the past and future evolution of the Earth. If you assumed constant continental area in those, how would things change?
The things change. We have a publication that tells us that the reviewer forced us to do this investigation. They change quantitatively. Maybe you have quantitatively, but not qualitatively.
Jeremy?
On the biological side, I find that you have significantly underestimated the prokaryotic world. And I see that in a couple of ways in the first part of your talk. You have today's world being the carbon being tied up in only 1/3 to the prokaryotic world. Whereas all the calculations I know about say the majority of the biomass is prokaryotic today. You also have a graph that shows the complete disappearance of prokaryotes at some point today or in the near future, which doesn't make sense to me. And so I'm wondering, in underestimating the prokaryotic world, how that carries over into the second part of your talk. Have you underestimated the number of habitable planets by prokaryotes?
First, to the first part of your question. The number today, the biomass from prokaryotic part is about 1/3. I don't know if you speak about the deep biosphere.
I include that in the Earth.
If you
yes.
include the deep biosphere, of course, but our model is for the habitability at the surface of the Earth. So if you include the deep biosphere, you are completely right. I must
Do you include the deep ocean?
Also not. You know, this is a box model where the ocean has all in its parts the same temperature. It's not in specially resolved mode. And the ultimate lifespan, according to this, is 1.6 billion years for the prokaryotes. And I cannot say if, of course, the numbers will change if we make a more developed model for the prokaryotic world, but maybe in the case that even the number of prokaryotic worlds goes up if we make it more robust. You know, in our model, the biosphere has only two limits, namely the temperature tolerance window, and secondly, there must be enough CO2 for the prokaryotes are robust that they can live also at very high CO2 contents of the atmosphere in this model. Only the complex world is sensitive.
So I find that you've been conservative in your temperature range. So if you reverse that position, then I'm wondering how that translates to the rest of your conclusions. If the number of prokaryotic worlds potentially goes up.
And this would be in the right direction because we think this ratio from experience should be larger than. This is only a lower bound. But to our knowledge, it was the first quantitative estimation of this rare earth problem.
Your temperature curve for the Earth in the first part of the talk, I think you had between sort of 2 and 3 billion years, you had temperatures of 40, 50, 60 degrees. But there's evidence for glaciations in that period. I think as far back as there's glaciation at 2.9, and then there's a major glaciation.
We have also here in the Neopotterozoic we have the snowball Earth and so. But
there's also evidence for a snowball Earth much further back.
But this is really a very long scale temperature that is called. You know, even here we had glaciations. But this is not included in this model. This is a geological background temperature. But at least there's evidence from Knaut and Löwe that at this time we had very, very high temperatures in the ocean surface from these oxygen isotope ratios here in the Archaean.
In simple basic world models, the existence of a biosphere on a planet extends the habitable lifespan of the biosphere. Is that true in all of your models as well?
Yes, we had some discussion, and for example, here we have a so-called Gaian feedback, because here, when there are the conditions for the existence of the complex life forms, they appear, and of course they take out CO2 from the atmosphere for making their biomass. And when they take out CO2 from the atmosphere, they even have this additional forcing of weathering, this beta 3, and so we have a negative feedback that makes this jump. So this is, in our sense, in the paper we also discuss it, it's Gaian-like. But only here at this point.
The new discovery of super Earths seems to extend a new class of planets that could be habitable. On the other hand, as I understand it, there's a group out of Rice who has suggested that anything over a 1.1 mass Earth will have stagnant lid tectonics. such as Venus, because you cannot do plate tectonics. So these seem to be mutually contradictory. Have you thought about the super Earths or the effect of tectonics?
Yes, and my doctoral student Christina Brunama did a thesis about this, and using these evolution models. And I know the problematic, but as I remember, the group from Harvard of Valencia and others, they propose that super Earths have a more probability to have plate tectonics, but there is another publication that says they have no plate tectonics. We cannot decide. In our model, we assumed a super Earth is an Earth-like planet with the chemistry of the Earth, with between 1 and 10 Earth masses, and with plate tectonics.
Just being clear, at ASCICON last week, we had several presentations, one by Nova State and one by Diana Valencia, and they both came down on the side of super Earths having plate tectonics. So they're against the minority group. So it is controversial, but it seems like more people are assuming it. Well, he said he said it's still very controversial, but he used very simple arguments. He said it's probably like the
And if I may add a further comment to this, maybe you read in A&A, Astronomy and Astrophysics, our paper on the Gliese 581 system, where, 1 year ago, the French group published a paper that they found a second Earth in this system, the Gliese C planet, and we investigated the system really with our model of super Earth, found that Gliese C is outside the habitable zone, but Gliese D, the more far away, could be at the outer boundary of the habitable zone. This was also reported in Nature, in a report like here. And so I can give you this paper.
Tom, do we have anybody on video?
Using the diagram that's on the screen now, perhaps could you just quickly explain how you parameterize the prokaryote reservoir size, for example, between 3.5 and 2.5 billion years ago? No, on that exactly.
No, this is the parameterization. Prokaryotes, we have always the same parameterization. It changes not with time. This is a disadvantage, because biologists told me you say C4 plants, but in future we may have C5 plants that have, for example, a lower limit of photosynthesis, which is much lower than now. But it is not so easy to predict evolution. And so, therefore, our model has always, over the whole time, the same parameterization for temperature and CO2 effects.
Okay, well, let's thank Siegfried again for coming on this way.